Okay. Well, so welcome to Dave and David and David and Donald and Harold, Joe, John, and Rich. Uh, Happy holidays to all of you, and glad you had a chance to take a break this afternoon to look into charging these electric vehicles that are beginning to fill the roads around us, along with a few other types of vehicles. Um, I'm going to suggest for communicating, we've got a uh, relatively small group. So let's do the following. If you have any technical issues to deal with the host, then please type those into the chat box. Otherwise, uh, there's two ways you can, participate in the discussion if you like. One is to simply open your microphone. I'm going to ask the host if you'll please make sure people are able to open their microphones. Open it when you're talking, but otherwise close. Otherwise, the echo problem that can possibly happen with two mics open at the same time. And otherwise, use the Q&A and type in a Q or whatever in the Q&A box, and we'll take a look at that. Usually it flashes at me when somebody has a question. And question means question, comment, whatever you feel like you want to type. Okay, so with that, let's get started. The session today is about charging electric vehicles, and particularly um, how that's done, what kind of charging is possible, what are the best ways to do it in certain locations, what are the code requirements, and so on and so forth. Uh, it would be useful to me to have some idea of the background of the folks in the participating today. So could we maybe just everybody start with Dave and open your mic and let us know what is your background, your electrical, mechanical, structural, still working, retired, or whatever. And do you have an EV or do you work with EVs in any way? This helps me to establish some of the details we cover, some that we can assume everybody knows, and so forth. So, Dave, David Plum, can you get your mic open up there and give us a quick rundown? Um, the alternative is if you'd like to just type something in the Q&A of what is your background, mechanical, structural, civil, electrical, and your specialty, whether it's buildings or uh, structures or uh, whatever, whether you're working for a company or whether you're working as a consultant engineer. All that would be useful. Let's see. There's something popped up in the chat box. Let's see. Oh, okay. We can't have all unmuted. So just raise your hand if you want to be unmuted. Okay. And I see Dave is a civil guy, works on structural buildings, and Mike not working. John is mechanical. Been in the business for a little while, 45 years. That's a long time. And here is civil engineering for a developer, owns grocery anchored shopping center. Okay. Boy, that's a good place for people go in for an hour to shop for groceries and plug in their electric car and have enough electricity to drive home with all their groceries again. We had a Whole Foods that did that, and then they took it out, and I'm not sure why. Um, let's see what else we got here. All right, so it said I'm speaking softly, so let me get a little closer to my computer, see if that makes a difference. Hopefully so. And anybody has a comment to make sure that I'm speaking sufficiently loudly and clearly that you can understand what I'm saying. And I use the word understand because it's often possible to hear without understanding. It happens to me all the time. Okay, so typed in Q&A for Dave. All right, let's go there. Okay, here's 4 of them. Okay. All right, Dave Jones, Forensic Electrical. Oh, that is a fun job. Wow. Wow. Yeah, that's a lot of fun trying to make those attorneys happy, uh, even if they're wrong. Harold Harkinen, Electrical Power Systems Engineer, 35 years experience. Fantastic. Okay, several EV charging station failures. That's interesting. I'd love to hear a little more about that as we progress through. Uh, Electrical PE, 27 years. Commercial buildings, usually 24 dual chargers max at each new building. Well, that's 48 cars, depending on the building size. That's not half bad. Great. It'd be interesting to see if what we talk about today is the means that you normally use. I'm guessing you probably use level 2 chargers that talk to each other, maybe, but let's find out as we get there. All right, this is fantastic. Thank you, folks. Appreciate that input. And so at this point, let's get going. You'll click a few boxes so I can see my screen. And so as you see, a few examples of electric vehicles here, from buses to smaller vehicles to uh, everywhere in between. And what I missed there, of course, is the scooters and the bicycles and all unicycles and so forth. But in any case, things are different now than they used to be. We got things like that guy in the lower right-hand corner on the road, and these couple of two across the top, they're not there much anymore. But we're seeing a lot of cyber trucks down in the neighborhood here. And some people are spooked. You get the black ones are kind of spooky, but still, they're interesting trucks. And from charging standpoint, they are at the top of the line because they go both directions. Um, so let's talk about, get a little background here, because why talk about something if there is no such thing, unless you really want there to be such thing or something like that, or writing a fiction story. But these are projections that the Edison Electric Institute made for United States electric vehicles in 2018 through 2030. Notice that 2030, well, let's say 2025 here. Maybe this was projected back in a few years ago, but the projections were pretty close. For 2025 was pretty close to 6 million on the road, but the estimate is that by 2030 we're going to have 3 times that many on the road. That may or may not be true now with the incentives going away. On the other hand, when you look at the possibilities for charging and the cost of operation and a few other things, and the performance of an electric vehicle, uh, people are still kind of catching on and buying those things. I see quite a few in the neighborhood down here. So I think it's definitely worth talking about charging them, make sure that I have a feeling most of us are on the same page in terms of what the NEC requirements are. But I'm going to go through all that stuff just to make sure that anybody designing electric vehicle charging stations will hopefully be aware of what some of the considerations are. And anybody thinking about it, even more so, will be aware of what the considerations are. In any case, if this Edison Electric Institution projection becomes reality, it means you're going to need to have ways of charging these EVs. And they need to be located somewhere. Now, most of them will probably be located in the garages because in a single family detached residence, um, generally there's a 20 amp, 120 volt outlet kind of sitting there waiting for somebody to use it. And what better thing to plug in a level 1 EV charger? And it takes a little while longer, but overnight, for most cases, it'll do the job, get all the electricity you need. We'll look at some of the numbers. Um, Parking areas, next thing though, I've seen that in quite a few places, both within the United States and outside the United States. And some of those, I guess, in the group are doing that. And it kind of depends on how much power is available in that parking area. If you got the power available, why not charge up a few cars? Because oftentimes those cars like to be charged at night when the utility is really happy to charge a car. So lodging, especially if you got a motel with EV chargers, that uh, more and more is going to be attractive to those driving electric vehicles who can park and add an extra 250, 300 miles overnight. That's fantastic. Because if you leave home and you're 300 miles away, you can't very well go home to plug in at night. You're going to need someplace else to do it. And so if you got a motel that can give you 10 hours of level two charging, you can put on not a lot of miles the next day. We'll look at some of those numbers. Um, and I say this one with tongue in cheek because I live in a condo, and of course we have condos on both sides. And even up to last year, the condo to the south of me, if you had an electric vehicle and if you dare plug that into a wall outlet in that building, it was a $250 fine for doing that. So that just indicates some of the the uh, the mysteries and misinformation that's out there on what electric vehicles will do to a wall outlet or a building's electrical ability to supply power to the rest of its customers. So anyway, there's a lot of hype out there. There's a lot of misinformation. We're going to try to put some of that to bed today. Um, so if you've got any interesting stories to tell relating to that, we'd love to hear them. So please, at some appropriate time when it seems like the right time in the presentation, feel free to raise your hand so you can get unmuted and then uh, describe the situation and how what you're doing is related to what we're talking about. Okay, so I laughed about the condos thing. I'm happy with we have a plug-in hybrid with that we've had since 2018, and we've been plugging it into a regular 120 volt outlet at night because we don't drive very far, 20, 25 miles a day maximum usually, and mostly use electricity, getting about 1,500 miles a gallon, so to speak, for the times when we have to use some gas to add some distance. But uh, our building is on a general service demand rate, pay about 8 cents a kilowatt hour right now for the electricity, and they have not argued the point that I'm plugging in, and they haven't tried to figure out how. When they found out that was all it was costing, they figured it wasn't even worth it trying to keep track. So, in any case, condos are an interesting challenge. We're going to look at design examples because sooner or later they're going to wake up. Condos are kind of similar to a parking garage, but not quite the same. So we want to look at different kinds of occupancies and what the requirements might be. Okay. There, of course, there are two types of electric vehicles, the all-electric and then the plug-in hybrid. Um, Here's some details. And if you want copies of these slides, the host does have PDF copies of this set of slides, so feel free to ask for them. You're welcome to use them any way you care to use them, reference or otherwise. And if you find anything that's incorrect, I would welcome your feedback on that because I've worked, some things are in the National Electrical Code are up to interpretation of the local authority having jurisdiction. And there are one or two items here where one could argue that Roger is maybe not quite right on. So I want to make sure we take a careful look at those as we get to them. All right. But in any case, with a plug-in hybrid, just, well, you can read all this stuff, and the whole thing is that electric vehicle is only electric, but the plug-in hybrid has gasoline backup. In 2018, that's why we bought it, because there weren't very many electric vehicle chargers outside our own garage. So we thought that extra 350 miles of backup of gasoline might come in handy someday. And every once in a while we use 20 or 30 miles of it. So anyway, that depends on who owns the car, obviously. So if we look at the code requirements, NEC 625.2 says the following vehicles are EVs. And that means automotive types, basically. You have to drive on the road because electric golf carts and forklifts are driving on golf courses and in warehouses. So if they're not on the road, then they don't count as EVs. The other thing is they have to use rechargeable batteries, so therefore try to use something like this in them, probably won't work because they're not rechargeable. So let's just take a quick look. Fuel cost per 1,000 miles. Again, background, because somebody's not going to buy an electric vehicle unless they have some reason. There's all different kinds of reasons one might have, but one might be fuel cost. Let's do a little comparison here and see what it looks like. Um, and we're going to have two assumptions: $4 a gallon, 15 cents a kilowatt hour. Fortunately, the math is addition, subtraction, multiplication, and division. Generally, engineers are pretty good on all four of those, and you may need to change some of the assumptions for your own location here. So if gas isn't $4 a gallon, put some other number in. If your electricity is 30 cents a kilowatt hour, obviously it changes things a bit. So, but the idea is let's compare the cost of operating a gasoline vehicle and electric vehicle because a lot of people might want to know about that. So if we have a full-size SUV at 20 miles per gallon, that's going to cost about $200 to drive that thing for 50 miles or 1,000 miles. If we got a baby-size SUV, then it's only going to use maybe 33 and a third gallons. So we've already saved almost $70. And if we get a regular hybrid sedan that gets 55 miles per gallon, then the operating cost is down to $72.80. And one might argue, how can you beat that? Well, maybe if you get a regular EV or plug-in, if you got 15-cent electricity. And by the way, some people are paying twice that during daytime hours, but those who pay that kind of money during daytime hours often can get on a time of use rate for EV charging only, where you can charge during off-peak hours and get a whole lot lower rate for charging your car. And those of you who've done some EV charging, you've done that research, you already know about that. And of course, every service, every utility service area is a bit different. So you need to check with your local utility on what they've got available. In any case, if you're using 15-cent electricity at 4 miles per kilowatt hour, then that's going to cost you $37.50. Now, 4 miles per kilowatt hour kind of says you're not going to run your air conditioning much. You need electrical uh, radios and other things in the car, and that's not very highly likely. So if you start using some of those, or if you're driving in traffic, a lot of start-stop, you might get 3.5 miles per kilowatt hour. 4 is what Tesla tends to use. They use 400 miles for their 100 kilowatt hour battery pack. But we found with our plug-in hybrid that 3.5 to 4 is a reasonable number over our 8 years of experimenting with it, 7 years, sorry. And in any case, also our electricity is more like 8 cents a kilowatt hour rather than 15. So instead of 37.50 for that 1,000 miles, we're paying less than 20. So in any case, in this particular situation with $4 gas, it turns out that the electric vehicle is the equivalent of something like 75-cent gas or so. And of course, if we have a plug-in, it goes half and half, then you're probably going to spend $58.75 overall. Now, one might argue, well, why go electric at all? And people have a lot of reasons. One is, well, electric, electricity doesn't have any exhaust. It doesn't pollute, doesn't dump that 18.6 pounds of or 19.6 pounds of carbon dioxide per gallon into the air, and that's being friendly to the environment. That's one argument. But others will say, well, wait a minute, your electricity is not CO2 free. I mean, they're burning some kind of fossil fuel, probably, at least part of it. So we need to take that into account when we talk about the environmental impact, but we're looking just at the economic impact at this point. So if we look at the CO2 part, it looks something like this. 10,000 miles for an electric vehicle on renewable electricity, meaning the new renewable electricity generated by wind, solar, hydro, or some geothermal or whatever renewable means is available locally, then we get no CO2 released. We get about 15 cents a kilowatt hour, if that's the cost of it, if we're buying it. If we're making it ourselves, then the cost per kilowatt hour is probably going to drop down below 8 cents in terms of the amortized cost of the system that's making electricity over the life of the system. What would you have to charge for your kilowatt hours in order to, and what would you have to charge for those kilowatt hours in order to pay back your system? On the other hand, if the electricity you would be buying if you didn't have that renewable source would be 15 cents, and in effect, you're saving 15 cents even if you have the renewable. So, except that you've got some cost for the renewable, so maybe you're only saving the difference. In any case, you use about 3,000 kilowatt hours, and so your fuel costs about $450, and there's no emissions. And the electric vehicle batteries could be available for the utility to dump extra electricity at a preferred rate into them if the vehicle's at a charging station at, say, noon when the utility has extra solar. So that's your renewable electricity picture, and if you got gasoline, the picture is a little different. It looks like this: 400 gallons of gas. This is for 25 miles per gallon, sort of an average thing for everybody. About $1,600 of fuel and 7,840 pounds of CO2. And that's at the 18 point or 19.6 pounds per gallon. And that happens to be 3.56 metric tons. And if you do this for 275 million of these on the road, that adds up to a bunch. That's like 2.16 trillion pounds of CO2, which is why transportation is the major contributor now to CO2 in the atmosphere in the United States. Vehicles contribute more CO2 percentage-wise than any other source of CO2, counting electrical generation, commercial, industrial, and residential, and agricultural. So CO2-wise, well, we have to be realistic. In fact, that electrical generation on average around the country averages about 0.92 pounds per kilowatt hour. That's a mix. U.S. Energy Information Agency, this is the data they had in 2019. It's gotten a little bit better because most of the newer electrical additions in the last few years have been renewable. So it's probably closer to 0.9, maybe a little bit less, but 0.92 pounds per kilowatt hour if it takes you 5 kilowatt hours to go 20 miles, then you can see that that's 4.5 pounds per 20 miles rather than almost 20 pounds for 20 miles. So we're looking at 75% reduction by buying your electricity from the utility with this 0.92 pounds per kilowatt hour. So there is certainly an advantage CO2 wise by buying utility electricity, and particularly since utility electricity is getting cleaner by the year. So next, quick look at charging levels. I think everybody's pretty much aware of this. Level 1, use a 120 volt outlet. So that means you can charge up to 16 amps because the charging is considered continuous. So therefore, you can't use the full 20 amps. You're only allowed to use 80% of that 20 amps. Or in other words, your circuit breaker has to be 125% and your wire rating has to be 125% of the rating of the charger. All right, so on a 20 amp circuit, you could charge at 1920 watts. Level 2 is 208 or 240 and can be charged anywhere from about 3,800 to 19,200 watts, depending on the size of the circuit. The largest ones out there right now for level 2 are the 80 amp at 240 volt, which is 19,200 watt overall. And the 80 amp is probably not one that too many people are actually going to use. The 32 tends to be the most commonly installed level 2 charger at the um, residential level, with the 40 amp pretty close second, and maybe the 40 and 32, maybe they're almost neck and neck. Kind of depends on the service size and what's available in terms of extra space in that load calculation. Level 3, they range to 50 kW to 350 kW, and that means you're looking at really big services, and so it's not something you're going to do residentially. Also, just a quick note that the level 1 and level 2 chargers charge with AC, but the level 3 chargers charge with DC. The batteries themselves, of course, are DC, so therefore the car has to have a equivalent of battery charger that converts AC to DC to charge the batteries. And they have that because that's all part of the battery management system in the car that makes sure the batteries don't go overcharged. Okay, so how long does it take to charge? Another question. Some of these you already know the answers. Those of you who know the answers, you're allowed to take a quick nap. But if you have enough for sure, then might as well take a look at these. Generally, you get 3 to 4 miles per kilowatt hour. The Cybertruck gets a little bit less than that. Electric bike, golf cart, whatever gets more than that. But still, if you use 3.5 to 4 miles, that's a reasonable guideline to use for a typical, not too big electric car, a standard sedan, or even a small SUV. So again, it depends how it's driven. If you speed up fast from stop signs, then you're losing more to resistance losses in the batteries because you're draining a lot of current to get that acceleration. And if you stop fast at a stop sign, then again, you're wasting some charging because you're trying to charge fast from a fast stop with your regenerative braking. And you don't get all the possible electricity unless you come to a slower stop. But if you drive carefully and economically, getting close to 4 miles per kilowatt hour is pretty easy to do. So, level 1 charger on 1,800 watts, you get about 6 miles per hour of charging. If you're running that thing at a lower on a 15 amp circuit, then you're going to get about 5 miles an hour. So a conservative estimate for a level 1 charger is 5 miles an hour Well, in other words, every hour of charge puts 5 miles more into your batteries. So if you want 50 miles, you plug it in for 10 hours overnight. And if you think about it, 50 miles a day for a year, that's over 18,000 miles a year. So, 365 times 50 is over 18,000. Most average driving is more like 12,000 miles a day. So most people can get by just fine with level one charging overnight. So level two, if it's charging at 8,320 watts, then that's 8.32 kilowatt hours per hour. And so here we're looking at about 30 miles per hour of charging. So if you drive 30 miles a day, plug in for an hour at night and you're done. And if you live in a condo and you drive 30 miles a day and you got six other people who drive 30 miles a day or 10 other people who drive 30 miles a day, if that circuit can be shared with smart enough chargers that talk to each other to limit the current, then they can pass back and forth with each other. And overnight, you can charge 10 different cars for 1 hour each and give 300 miles. So 30 miles each to 10 different cars. And this is something is all communication protocols in place for that. National Electrical Code allows up for that. There's special provision in Article 625. So uh, that's the clear way to go in a condominium where people tend to be plugged in at night and leave it there all night. And almost nobody's going to use it all up at night. If that happens, then somebody's going to do a little negotiating. But, these things can be programmed a number of different ways in terms of how to share that electricity. So, level three, that's 63 kilowatt hours in a half hour. And so that's a little over 210 miles in a half hour. Well, you stop for your sandwich at a McDonald's or something like that, a fast food restaurant, spend a half hour, uh, use the whatever restroom is appropriate, and walk out, and you got another 200 miles before you have to stop for whatever you might have had with that hamburger, maybe the shake or the dessert. But in any case, the other thing we need to remember is that at about 80% fill, charging rate slows down a little bit because the batteries get a little warm when they're charging fast, and they have to be allowed to cool down to room temperature, whatever that is, in order to properly calibrate the charge at 100%. So that's why cell phones and all other things with rechargeable batteries, this charging rate slows down at the end. But the 63 kilowatt hours for a 100 kilowatt hour battery pack is less than 80%, that's 63%. So that's okay. That's going to charge pretty fast if you don't hit the 80% mark and put in. And if you hit the 80% mark, then you've come pretty close to putting in as much electricity in the tank as a person's going to want before they stop again anyway. So, what are some important observations? Well, if you drive a typical EV, 10,000 miles a year, that's 27.4 miles a day, so let's say it's 30. Well, what does that mean? It means level one, you got 5 hours a day of charging. Level two, 1 hour a day. So, if we have excess renewable energy at noon, uh, wouldn't the power company be just happy as a lark if you would plug in your EV and charge it up at noon so they don't have to curtail that extra renewable energy that they're generating for free? Because after all, sun doesn't charge, there's no fuel charge there. So you want with any renewables, you want to milk them as far as you can and use every drop of electricity they're going to make. So why not save some of it in some EV tanks or EV batteries? Um, and maybe even offer the EV drivers a special rate for buying the electricity at the right time of day. Okay. And so let's just say a system is available for 18 hours a day. Again, the math is pretty simple with load management. That means you can charge 3.6 EVs a day at level one on a single circuit to get their average daily 10,000 miles, okay? Or their annual 10,000 miles a year. If you have level two 40 amp chargers, then you can charge 18 EVs a day because 1 hour a day gives them their 30 miles a day of driving. Okay, so the various manufacturers of EV chargers are aware of this, and they have lots of protocols out there so they can talk to each other and divide up the electricity so everybody's happy by the time they're ready to get in their car the next morning. So useful to use these observations as we look at some basic design rules based on National Electrical Code. Chargers, there's a number of different ways they might be configured. The basic ones, this is what you're concerned about. And of course, the one that comes with the car, it's obviously going to be compatible and it's going to talk properly, and charging time is going to take whatever it takes, like the 5 miles an hour. Installation cost is almost zero if you've already got the outlet in your garage. And they're totally safe because they're all UL listed. So, well, that makes it at least safe enough as far as UL is concerned. And they're probably going to look like this. And again, this is probably not too unfamiliar to the. In fact, let's just stop right here. How many people? Let's go. Let me take a look at the oh yeah, we got five comments here anyway in Q's and A's. Let's take a look. Uh, okay, consulting power systems. Okay, those ones we asked about earlier. Okay, now what I'm going to ask you to is how many of you actually own electric vehicles? So this is just old information. So if you just all you need to do in the Q&A is raise your hand. And wait a minute, you can't raise your hand in the Q&A, can you? No, but you can. I think you can raise your hand in the chat. Oh, Ford just announced they're canceling the EV division. That's interesting. Uh, wow, and those hot Mustangs. I wonder what's the deal. No EV in your house, no EV. Okay. Anybody else have an EV? Do you have any friends with EVs? All right, so maybe this information is relatively new then. Okay, all right. Well, we're going to stay with that. Okay, let's see. I'm doing a little quicking here just to clean up some of the items. Okay, so here's your basic charger. Well, here's the pin diagram. The big ones are where the power comes in. The interesting thing is the charger doesn't care. This is AC, and it can either be 120 or 240 volts or 208 volts. The charger in the car recognizes the voltage and cuts it down to the proper DC battery charging voltage automatically. The other big hole at the bottom there is the ground. And if the thing isn't grounded, it's not going to work. It's absolutely insist on having a system ground. And the other two smaller ones are the uh, called proximity detection, but basically it's communications, and it tells the car that it's plugged in. And if you try to start it and drive away with this thing plugged in, it won't let you do it because of the communication there. So you got to get out and unplug. Um, but it also might connect to your cell phone so you can dial up the app and see where the next charging station is or how much charge you've got left before you're going to be full or whatever. So convenient, and those two little communication holes there are pretty important, and particularly for future use when they'll be able to talk to the utility directly. The advanced charger will be bidirectional. These are in all Cybertrucks right now. Cybertruck is capable of sending electricity back to the grid if the grid asks for it. There are other advanced situations where in some of the Ford F-150s, for example, you can get house power, you get 60 hertz house power, but you can't feed it back into utility lines because it's not UL 1741 approved for connecting back into the utility, or that's IEEE 1547-2018. Excuse me. But bidirectional is going to be a big deal. If not here, it's going to be elsewhere. Adaptable, portable, and smart. It could be helpful in billing, load management, it can be networked, and a lot of other things are possible with the advanced chargers. And one of these days, we're probably going to see those start popping up out there. For level 1, level 2 chargers, level 1, here's one that just plugs into the wall. This is the kind we've got with our vehicle. And this one probably draws 12 amps out of 15 amp circuit. Actually, it's a 20 amp circuit, but I think it's only pulling 12 amps. This one is about in 8 years. The only time it's popped a fuse is when somebody's plugged in an air compressor on that same circuit. And we quickly recognized the issue, and they were told to please unplug the car at any point where you want to plug in your air compressor, and that solved the problem. No big deal. So here's a level 2 charger on an outdoor pedestal. Looks good in front of an electric vehicle dealership. Wall-mounted level 2. Notice the communication antennas there. Ground-mounted level 2. This is a local library. And another ground-mounted at a local university. For those who haven't seen what they look like, and I think we'll have some level 3 pictures here. McDonald's loves them because they bring in a lot of business. You see here the simple one that shows the ground and two communication on top and the two big connectors for DC on the bottom. Or if you let this thing be universal, so it'll do DC or AC, you simply add two more pins. And those two pins, as you notice here, contact 1, contact 2, they can be either 120 or 240 and give you level 2 charging. So this one will charge either at level 2 or level 3. So what are some of the applicable code standards and abbreviations? Got to get those acronyms in. Otherwise, we don't sound like experts. So let's see what we can do here. 220.87 and NEC 625 are kind of important, but there's other 220 references also. There's a bunch of NEMA stuff on the configurations of the connectors. There's ESAE J1772. And that's the standard for EV charging equipment that you saw those chargers that look like gas station things, because after all, you want your electricity to look like gasoline to the car, otherwise it may not want it. And then there's the Open Charge Point Protocol, which enables communication among chargers. As mentioned earlier, if the chargers can talk to each other, they can do load management, current limiting, all sorts of different sharing of one circuit to make sure the circuit doesn't get overloaded. All it takes is a single or maybe two, depending on the situation, If it's all electric vehicle charging at 208 or 240, then you can get by with a single, uh, uh, boy, I lost the word. Um, oh, that thing you wrap around the wire to sense the current in the wire. I'll think of it when I quit trying to think of it. A single sensor will tell you when the current in the wire has reached its maximum allow, which would be 75% of the breaker size, and it will slow down the charging to however many charges it has to slow it down according to whatever algorithm is there. UL 2202 is a standard for EV's charging systems. So if you're going to build an EV charging system, it has to be listed to UL 2202. And you can buy one of those UL 22s for a mere $1,000 if you want to know what it says. Uh, I thought I'd just mention that for anybody who might want to buy one. I didn't have room on my bookshelf for one, so I decided not to get one. UL 2231 is the standard for personal protection systems for EV supply circuits. Well, okay, yeah. Maybe on certain EV supply circuits, if you have 1,000 volts DC somewhere for level 3 charge, you probably want to be a little careful with that. So you got some standards on that. And there's the North American Charging Standard. And that's what Tesla and Aptera have been working on, trying to get single conductor for everything. I'm not sure whether we're there yet on that. I'm not sure. And some of the older connectors that are only good for level 1 or level 2, I think, are going to be around for a long time. Anyway, this Green Carports website has a lot of good stuff. So if you're interested in more details, go to that website and it'll fill you in a lot of information beyond what we're talking about here. Okay, a little more 625. Point 2 defines EV storage battery as one that's sealed and does not release gas. That's important because that means you don't have any extra ventilation in your garage. Fastened in place. It can be removed without a tool. If it's fixed in place, you need a screwdriver to get it loose or something else. Uh, and nominal AC system voltages. Notice there are a lot of possibilities, and DC up to 1,000 and AC up to 1,000 for EV chargers. So that's a lot of flexibility there. EVSE and wireless power transfer. Uh, Not a whole lot of wireless power transfer, but there are some electric bus systems where they've got wires under the ground, under the road at bus stops. And when the bus stops at that bus stop, it automatically gets charged for the time it's parked there. And if you have enough of these, if you can get one more mile from one stop, uh, then you don't have to stop your bus. Every time it stops to pick up passengers, it picks up a little more electricity. So this wireless power transfer is interesting. I've not seen any wireless power transfer for regular passenger electric vehicles, but it seems to be something of great interest for buses. Um, Part 2 of NE 625 gives the manufacturing specs for getting something listed. So more 625.40, each outlet stalled for in charging shall be on a single branch circuit. Well, yes and no. Then there's the exception that says that if the chargers talk to each other, then we can arrange some load sharing. 641, 2541. So this is pretty useful because it says the branch circuit overcurrent protection must be rated at 125% of the equipment rating. Okay, that's fine. So if the equipment rating is 40 amps, then the overcurrent protection must be rated at 50 amps. That's pretty straightforward. Feeders rated at 125% of continuous load. Okay, well, that says plus 100% of non-continuous. And this means different things for residential and non-residential. But in any case, it says the feeders to, now what are the feeders? The feeders are not the feeders to the charger, but they're the feeders. Now, well, this is kind of open for interpretation, isn't it? You can have feeders going to a single circuit. On the other hand, the feeders to the distribution panel presumably are rated at 125% of the continuous load on the panel plus 100% of the non-continuous load on the panel. So this is one that is open to interpretation. Of course, your local authority having jurisdiction will be happy to let you know how they interpret it, and then you just follow what they say. Now, distribution panel bus bars are rated at 100% continuous. That's significant to know that. So it means the feeders to the distribution panel need to be rated at the 625.41. So in other words, if you got 2-aught feeders feeding 200 amp bus bars, that doesn't necessarily mean that your feeders are rated at 125% of the load. You need to be a little careful about that if you're going to be really fussy and get it right. All right. So 43, equipment rated more than 60 amps. You can't have it plugged. You have to have it locked in. You need a lockable disconnect on that. Can't just plug it in. And 44, all about the non-locking grounding receptacles. And 48 covers interactive systems, and it references UL 702 and NEC 702 and NEC 705. Now, 705 is the section of National Electrical Code that allows you to sell electricity back to the utility and gives all the rules for being able to do that. And of course, 705, in order to use 705, your equipment has to be listed to UL 1741. Anyway, this one is one that I've been watching really, really carefully to see where this goes. Because this could be a huge contribution to the utility for stabilizing utilities, and if it's done properly. 62550 says charger has to be more than 18 inches above the floor. And that's because if you unplug it, if it makes a spark, and if there's gasoline vapor in the garage, then you could lose your garage, and you don't want to do that. So make sure you plug it in more than 18 inches above the floor to watch out for that nasty gasoline vapor. And then a few more details on 625. And again, this is all 626 for electric trucks. So that's kind of new stuff now. Finally, we're getting some electric trucks. Some of all these delivery trucks out there. Wouldn't it be nice if all the mail trucks and all the UPS trucks and all the Amazon trucks would be electric? We're trying to minimize CO2 release. That would certainly be a big contributor to helping that problem. But that's a different webinar on climate change. In any case, 220.87 is kind of useful, and we're going to do an example of that because it's very interesting how that can work out. So let's do a service calculation for adding a charger, all right? We're going to use 220.83 for an existing single family and 220.84 for an existing multifamily. All right, so we're going to do two different ones. Let's start with a 1,500 square foot dwelling with no new air conditioning or heat, just a new charger. So what do? You list your loads because that's how you do a load calculation. You figure out what you've got. You start with your general lighting, 3 volt amps per square foot, and 1,500 square foot gives you 4,500. And then if you add up your washer, your dryer, all your appliances, circuits, and so forth, you get 13,900 more volt amperes. And then if you add your electric water heater and your electric range, you get 16,500. We could add separate lines for each one, but then my screen wouldn't have been tall enough. So, well, I kind of ran them horizontally instead of vertically. Calculation says, okay, this is existing. So for an existing, where we want to add something, we take first 8 kVA at 100%. So that's 8,000. Subtract that from 34,900. That gives 26,900, and take 40% of that, gets 10,760. And then it says you can, if you have 1 to 4 heating units, you can take them at 65%. So if you got 10 kW heat, and that's because it generally cycles no more than about 15 minutes before it turns off again. It's not continuous, so you get 65% there. There's 6,500 volt amps. And this one is possible your local authority having jurisdiction will require that on 100%. If so, you follow what they want you to do. Then your 7680 volt amp EV charger at 125%, it's a continuous load, 9600 volt amperes. And here again, this could be something you would discuss with a local AHJ, because one could argue that the continuous load of the 7680 VEV charger is 7680 VEV. And with 7680 volt amperes, you're going to have 32 amps, which would require a 40 amp circuit breaker. But if we take 125% to be conservative, add that 3600, our total is 34,860 volt amperes. Divide by 240, and we come up with 145 amp minimum service. So if you have an existing 150 amp service or more, then you're in good shape. Off you go. If you don't have that 150, then you start asking questions about, well, do we really need 125% of the 7680? And they may say, no, you don't really need 125, so you can stay with 7680. So instead of 40 amps, you can add 32 amps. And so instead of 145 amps, you'd have 137 amps instead. So these kind of things are kind of negotiable because of some small level of ambiguity in the NEC, which might be enough to justify a conversation with the local building department. Anyway, it basically says that pretty much anytime you got 150 amp service, unless you got something really fancy like tankless water heaters, this 3 volt amperes per square foot for a residence is generally pretty high now, simply because of all the LED lighting. So therefore, and so if you measure and try to max out your current draw by turning everything on, it rarely comes up to the calculated load. So in any case, in this case, we would put a 2-pole 40 amp circuit breaker in the main distribution panel if there's room for a 2-pole breaker. And if not, you may need to do a line side tap or something, or one way or other feed a sub panel, new sub panel. All depends on the individual situation. So in any case, the load without the charger would have been 125.25 amps, but now with the this particular charger added at 125%, it increases to 145 amps. So this is a simple residential calculation, and because it's so simple, that means that in general, there wouldn't necessarily be a reason why an engineer has to get involved. An electrical contractor could submit this calculation. The alternate service calculation for adding a charger is 220.87. Let's see, at 3 o'clock, we got time. Okay. Because this says you can find the maximum demand over the last 12 months. Well, okay, but gee, on a general service demand rate, that's easy. But if you're just doing a regular residential rate where you only pay for kilowatt hours, it's pretty hard to know what the demand is. That means you're going to have to measure for 12 months. But the code says, yeah, that is kind of crazy. So here's the deal. We'll let you measure for 2 months, as long as you measure both line currents, and then look at the highest line currents under over that month where the maximum demand occurs for the year, which would probably be a month with your most kilowatt hour use. And you monitor both line currents, put your current transformer on each one. That's the word I was looking for before, and now that I quit trying to remember, I remember, of course. Anybody who's approaching my age is well aware of that kind of memory issue. So in any case, and we got a couple older guys here on this, so glad to have you here. So both line currents need to be monitored, and you take the larger of the two because obviously you don't have to have identical line currents when you got 120, 240 with neutral current. Then add the proposed new load to 125% of the maximum monthly demand and compare it with what you got with 220.83. And if it's less, go with the new one. But this is pretty impractical for residential and mostly not necessary. But if you're in a condominium, this story is totally different. So let's move up to something a little more fun. Let's look at some three-phase stuff. Okay, let's three-phase 120/208. Okay, and we'll ask a simple question: how many 16 amp 120 volt, in other words, how many 1920 watt chargers can it supply? Well, one way to do it is, since they're single phase 120, let's just connect them in and see what happens. So each charger is going to be on its own branch circuit with a 20 amp circuit breaker, okay? Single pole. And NEC does not have diversification factors for multiple charges, but it does have the provision for letting an external load management program take care of this job. So in a sense, this is why there are no load diversification factors, simply because you do that with your charger system. So if we got 200 amp feeders, this means the maximum load on bus bars has to be 160 amps or less. So in order to be at 80% of the feeder load. Balanced three-phase power, we know the formula. P is equal to 1.732 times, that's in other words, square root of 3 times the line-to-line voltage times the line current. Line-to-line voltage is 208. Line-to-line current, well, line current, individual line current is 160. And we're balanced at 160 on each line. So that says we can connect 57.64 kilowatts of EV chargers to this 200 amp charger, or this 200 amp three-phase panel. Okay, 57.64 kW worth. So how much for each one? Each one is 1.92, so that means we can have 30 chargers. All right, so 200 amp service will connect to 30 level 1 chargers, one per circuit, no sharing, no anything. On the other hand, if the chargers are able to share with, say, 3 or 4 other vehicles, you could conceivably be charging 90, 100 or so vehicles. If you're charging 24 hours a day and not doing any unreasonable amount of kilowatt hours for each vehicle, limiting each vehicle to something in the order of 10 to 15 kilowatt hours. Or even more, even 20, 25. So 30 charges, it's kind of convenient because in a three-phase panel, that's a nice balanced load, 10 charges per phase. So how do we know what the line currents are going to be, just to be sure? Well, 200 amp three-phase 30 position panel, 10 charges per phase is going to look something like this, except again, my computer screen is not long enough, so we can only do it for 12 of them and then assume it will work for 30. If we put 1920 VAs on each of 12 chargers, we get 23,040. And we got 16 amps. And this, this maybe looks familiar on how you've drawn up three-phase panel load calculation, 16 amps for phase A, 16 for B, 16 for C, then back to A with 16. So, whoops, I went too far. I got to move this little black box. The bottom line is we get 64 amps on each phase if we have 12 chargers operating simultaneously. So let's see, 12 times 12 times 16 times 120 is 23,040. That adds up nice. 30 chargers then, instead of 12 times 16 times 120, we'd have 30 times 16 times 120. That's 57,600. And that's exactly what we wanted. So level one chargers, no big deal. Just connect them right on in, make out your panel schedule like this, and you're good to go. Level two, however, is a bit different, and that's the one I want to look at carefully. Alternate method for 120. All right, so fine. We connect them like this. Just to show that as you connect in these single phase chargers, balancing everything, you're looking at the line currents on the upper right, over on the right-hand side there. And after we've got three chargers in, with all the line currents balanced, the neutral current is the sum of the three line currents. And assuming that there are no harmonics, assuming this is a nice sine wave and the neutral, and there's some utility jurisdictions who have some question about whether that would really be the case. So they are a little fussy about measuring that neutral current. But in any case, the line neutral currents are supposed to be 180 degrees out of phase, and they will be, or sorry, 120, and they will be provided there at 60 hertz. And they will add up to zero at the 60 hertz component of whatever waveform is going through. However, the third harmonic will not add up to zero, and some of the others won't either. So it is something that some utilities have expressed some concern, and I have not read far enough to see what the field research has yielded on this. So if anybody has any thoughts on this, I'd love to hear. So anyway, this is simply a wiring diagram of how we connect those up. Let's, in other words, it looks like the neutral current never exceeds the largest line current. If it's not zero, even with harmonics, highly likely that it will not exceed the largest line current if we have an unbalanced situation. And of course, different chargers might have different waveforms, so who knows what kind of current waveforms we're going to have. Let's do 40 amp 208 volt chargers and see what we get. And I've seen a lot of cases where you see a diagram showing that we're going to hook the first one between A and B, the next one between B and C. We know each one pulls 40 amps. And then one from A to C, A to B, B to C, A to C again. And add it up, 160 amps per phase with 6 chargers. So let's see if this works. Well, let's do the math. For balanced three-phase system, the volt amps is going to be 1.732 times the line current times the line-to-line voltage. So if the line current is 160 amps and the line-to-line voltage is 208, then we're going to get 57,641 volt amps. But wait, this calculation shows 8320 for each of the 6 charges is only 49,920. What happened to the other almost 8,000 volt amperes? Well, and the answer is it gets hung up in this business about 1.732 and about this 120-degree phase difference. And that's why you can't just do it this way for a three-phase system, because you end up selling yourself short. You've really only used up less than 160 amps. Okay, how much have you? Well, let's take a look. Let's find out how much we really do use rather than 160. And we do this by taking a look at the chargers. Let's connect them up one at a time. We've got 3 line currents. If we put charger here, then we got 40 amps on A and C. If we put a charger here, we don't have 80 amps on A. We have 69.3 because it's 40 times 1.732. Because the current on A and the current on C are not, or the current on A and the current on B are not in phase. They're 120 degrees out of phase with each other, so they don't max out at the same time. And that's where the 1.732 factor. By the way, for those of you who want to play with this a little more, there's an appendix on these slides that if you get the set, you can look at the phasor diagrams and all that stuff if you love electrical engineering. But in any case, this is where the rub comes in. Now let's put the third one in over here. And now we got 40 amps on all 3 lines. So each of the 3 lines now has 69.3 amps rather than 80 amps, which one might think, since each one is connected to 240 amp charges. Okay, so 69.3. Well, if we put 6 chargers on, then we would expect the current to be twice the 69.3. And indeed, if we do that, we get 138.6 on each line instead of 160. Now that means we can add more. But can we add 3 more? And the answer is a resounding no, because that would put us over 160 amps if we added 3 more. Even if we added 1 more, it would put us more than 160 amps on one of those lines. Or maybe on 2 of those lines, in fact. So there's where the advantage of balancing the loads on 3 phases is very helpful. Have 3 equal loads, or 6 equal loads, or 9, or 12, or whatever. So in any case, here's our little arithmetic check here. 6 chargers at 40 amps at 208 volts is 49,920 volt amps. And with this balanced load, 136.8 times 208 times 1.732. In other words, I times V times the square root of 3, 49,920. So here we're good. So useful to know this when you're working with 3-phase systems, you can put in more than you thought if you were drawing it the simple way. You got to use this 1.732 factor. Well, you don't have to, but if you want to get maximum out. What this means is maybe we can't do any more 40 amp chargers, but we probably can hang a couple of 30 amp chargers, maybe 3, or maybe 3 20 amp 240 volt chargers. We can just see what it takes to go from 138.6 up to 160. All right. In any case, let's move on and take a look. Balanced loads we've got these two formulas that we can always use. Power is 1.732 times line current times line voltage. And of course, that's power. And of course, if there's any reactive power involved, then of course, then we don't say P total, we call it volt amperes total, which is really the key here. But the charges themselves are rated in volt amperes. So that's why we are using plain old current times voltage equals volt amperes. So if the loads are unbalanced, then you should always use the next higher balanced load. So if you have only one, you should assume you've got three. If you have four, you should assume you have six in terms of what your line currents are going to be. So if you're unbalanced, use the next higher balanced load as representing what your line currents will be. Okay? And if the power factor isn't unity, then you have to multiply the whole thing by the power factor, and that means your current is going to be higher um, uh, because of the power factor being less than 1. Okay, so what do we have? Keep loads balanced, and then what if we go up to 160? What are some of the options? Well, we're at we want to have 160, so what are we allowed? Well, maximum charges per current per phase would be the maximum charger current per phase would be 160 divided by 1.732, which would be 92.379. So 9 chargers at 32 amps each would be 96 times 1.732 is 166.3 amps. Close, but not quite because it's 6.3 amps over it. But what if they didn't use 32 amps each? What if they used a little bit less? If we could just take 1.21 amps away from that 32 amps, then we could use the 9 chargers. And of course, can we do that? Yeah, because some of the chargers, if they're smart enough, they can do that. So you want to check your charger specs and see whether it'll allow you to do that. So you could bump it up from 6 to 9 if you could reduce the current by a mere 1.21 amps or down to about 30 amps each instead of 32 amps. Well, 30.79 if you want to be more fussy about it. So once again, the call for demand management, very helpful to be able to charge more vehicles without having to go to a whole lot of bother of extra circuits. And so let's do a condo plonking area just for the fun of it. I happen to know this building pretty well. Happen to be sitting in the 5th floor of it right now. And happen to know that the common areas are served by an 800 amp, 120, 208 volt, 3-phase service. So ask the manager, could I please look at last year's electric bills? And of course, as cooperative as managers always are, notice the buildings on general service demand utility rate schedule and the last 12 months. And let's look at the biggest one over the last 12 months. And let's do 220.87 on it to see what we can do. And then let's just add on chargers until we meet the maximum limit. That sounds pretty straightforward, and make sure bus barn feeder sizes are consistent. So here's the bill. And look at that. There's your kilowatt hours and your demand kW, 84 kW. Isn't that fantastic? Now, that means we have to figure out from 84 kW, how many kVAs is that? All right. So, and furthermore, we can't take 84. We need to have 125% of it. So that's 105 kW. which we're going to interpret as 105 kVA because that's allowed by the code. That's what they're measured. That's what would be measured if one had a clamp-on ammeter or current transformers on the lines anyway. So it's 105 kW. Well, that's interesting, isn't it? What's the line current associated with 105 kW? Well, current is power divided by 1.732 times the voltage. That's 291 amps. Well, didn't we say we had an 800 amp service? Yes, we did, but we are only using, at the worst case in a year's time, 291, and that's even including the 125% that's required by the 625 code requirement of 125% of the maximum uh, peak usage. So 291. So we got 800 minus 291 left. That's 509 amps we've got available. What in the world can we do with 509 amps? Well, let's find out. And if we're going to be, careful and to the letter of interpretation, we would only use 80% of that, so we'd use 407 amps for chargers. Okay, assuming we're doing a continuous load type thing, we're going to share and let them charge 18 hours a day or something like that, except during utility peak time, but say 3 in the afternoon and 9 at night or something like that. Um, so I need you to please, I have to mute for just a minute here. And if anybody else needs a 1 minute break, we're going to take a 1 minute break, maybe 90 seconds, and I'll be right back. Okay, back again. Hopefully everybody enjoyed a chance to relax for 90 seconds or however long that was. I didn't set my timer. Anyway, let's try level 1 chargers and see what we can do with 407 amps because that's a simple way to do it. And how are we going to do that? Well, let's keep a balanced load, so we'll add 3 at a time. Okay, so we already know that the line currents are the some of the charger currents from last time. And therefore 407 amps is available. So if we take 407 amps and we got 16 amps per charger, that suggests that we've got 25.45 chargers. And that's not a total of 25.45, that's 25.45 per phase, or simply running it, kept rounded down to 25. So here's 75 chargers we can supply with 407 amps. And that's those 407 amps, 75 charges, these guys can be plugged in 24 hours a day, if indeed this 407 amps is available 24 hours a day. Or alternatively, if we were sharing and if we share each charger with 4 different vehicles, well, then we got 300 vehicles can be charged, depending on how much charge they need. So that's the part you got to start with is, well, what's the average charging going to be per vehicle per day? And from there, we can work our way into how many we can deal with. Okay? So we can do, without anything fancy at all, we got 75 chargers. And if we do other lower charging levels, more demand control, whatever, we can use a whole lot more. Okay, what about level 2? Well, let's see what that looks like. We now know we got to be careful about the 1.732, but if we add single phase chargers in multiples of 3, it looks like this. 3 of them, the line current is going to be 40 times 1.732 or 69.3. So every group of 3 is going to add another 69.3 amps to the individual line currents. And that's whether or not you've got a neutral here. Because these currents are line currents. No current flows back on a neutral in a delta connection like this. So therefore, 407 divided by 69.3 is 5.873, so we can put 5.873 chargers per phase. Well, I guess that better be just 5. All right, but still, that's 15 chargers. That's not too bad, but then we keep in mind that, my goodness, but 15 chargers, yeah, see, 346 and a half, less than 407, so that certainly works fine. It gives us some extra electricity for something else. But keep in mind that these 15 chargers, if they go in individual cars that go 30 miles a day, they're only going to operate for an hour a day. So if we allow 18 hours a day of operation, then we can use 18 times as many vehicles. So 18 times 50, that's almost 300. It's 270, isn't it? That's a lot. So what does it say? It says, my goodness, if you've got 407 amps available, you can charge an awful lot of cars. And if this 407 amps is available at a restaurant, then most cars aren't going to plug in for more than an hour. So depending on what time people go to the restaurant, they get a pretty substantial 30 miles worth of charge during their meal, maybe 45 if they have a couple of appetizers and a couple of drinks. And what a nice thing that the restaurant can offer by a few kilowatt hours worth of electricity if they're paying this on a general service demand rate at, say, even 10 cents a kilowatt hour. And somebody takes home with them 10 kilowatt hours of electricity along with their leftovers from the meal. That's only $1 worth of electricity. What a nice way to attract customers. It's almost cheaper than an ad in a newspaper. Maybe you need an ad in a newspaper to tell you get free electricity. Who knows? Anyway, but here, this is the math that's involved. if you're going to use multiple chargers on a circuit, or if you're just going to have 15 chargers without any fancy load management. And not only that, you got 60.5 amps per phase for other stuff like smaller chargers. So in a year of charging, 1 hour charging a day, you got 10,950 driving miles, which is almost average. In an older community like mine, I mean, we drive our car less than 6,000 miles a year, so we bring down the average. And it all depends on where you are. New York City, who drives their car very far in a year's time? Uh, a lot of them just kind of stay parked for a while. So it all depends on where you live. That's the big difference, and you're the one to make that decision. 10 hours at night, you can charge 109,500 miles worth of charging. That's a lot of charging in 10 hours at night during low utility rate hours. That makes your operation of the vehicle relatively inexpensive. So, interesting numbers. If you have 15 chargers operating 10 hours a day, 4,500 miles, 24 hours a day, 10,800 miles a day. Okay. Now that's not for each vehicle. It's for the sum total of all vehicles that are operating connected to these 15 chargers. But that's a lot of miles. And if you look at 10,800 miles, we looked at modern carbon dioxide associated with 10,000 miles is quite a bit. So you can save a whole lot of CO2 with the simple 407 amps worth. So then you look at, well, maybe we don't need that whole 407. Maybe we can just drop a 42 position 225 amp three-phase 12208 panel, and maybe that's all we need for the whole building. And indeed, if you do that math, you'll find that, yeah, that's more than enough. And most condos would never believe if you said all you had to do is put in a simple 225 amp panel fed with 4-aught feeders, and you can probably, I mean, if you've got a condo that's got less than, say, 50 or 60 people, if you got a condo bigger than that, then maybe it's going to have multiple buildings, each of which has about this number of people, or if it's a bigger building, it's going to have a much bigger service and probably about the same amount of additional power available. So there is a message here that's important, and that message is simply that in a condominium building or any building on a general service demand, the house load may well be, and particularly for condo, not necessarily for a restaurant, but maybe for a business, the house load with businesses now using a lot more LEDs and more efficient equipment, the house load based on the uh, annual load demand data may be a whole lot less than the distribution panel size. And if so, it's a good idea to plug these vehicles into the building service as opposed to the individual unit service. And let's take a look at why that's a good idea. Okay. You can also take note that a little communication among chargers is really useful because otherwise some of them might be sitting there not doing much at all day long. And why not use them if there's a demand for them? All right. And of course, you can mix level 2 and level 1. And I'm just going to click through this one kind of quickly because we got 100 and 215 amps left over that we can put some some level 1 stuff, or we could put additional level 2, whatever. So all matter what you want to do. But this part about connecting to dwelling services gets a little more complicated. And first of all, you can do that calculation about 220.83 or 220.87 and see whether these vehicles can be added to any one individual dwelling load and overload that one dwelling. And that comes out the same as if you were doing a single family detached. But when you start looking at, wait a minute, if the dwelling service comes from a meter bank, and likely it is in a condominium, then you're going to have these diversification factors. And you need to figure out what it is. For example, if you use the demand factors for 3 or more multifamily dwelling units, here are some of the demand factors. 8 to 10 units, 43% of the demand calculated for a single unit. 28 to 30 units, you're down to 33%. So, for example, in a building like the one we've been talking about, it turns out that this building has two 1,200 amp meter centers, and one of them services 21 units, and another one thus has a demand factor of 37%, and the other is connected to 22 units and has a 36% demand factor. So what if you start hooking in these electric vehicle chargers into these meter banks? The demand factors could maybe be applied. On the other hand, if these vehicles are going to be charging simultaneously, you could get in trouble. We've just shown that in the building itself, the issue is no big deal. If you're on the building service, the three-phase service, but for the single-phase service to the individual units, it's another story. Because the individual calculated load for the 21 unit load center is 1,057 amps. So if we start trying to add to that, and technically speaking, one would want to add the demand for each individual charging unit. If you do that, and also the 22 unit, the original demand is 1114 out at 1,200 amps. So we're pushing pretty close to the maximum demand here. Basis here is 24/7 occupancy of the units. In a lot of places, that's not true. You can take that into account, maybe, but it would be some very interesting engineering. And it'd be interesting to have some data on what the annual demands are for each of the meter centers individually, which may be hard to get. In any case, if you've got 114 amps available for the 20 unit center and 68 amps available for the 22 unit center, that's hardly anywhere near the amount that's available if you're able to tie into the main building house load. So if you consider the chargers in multiples of 3, it's not going to end up with very many chargers. So it's something to think about seriously. If anybody in a condo says people may have their EV chargers, but they're going to have to connect these chargers up to their very own house loads because we don't have any way of charging for the electricity. Well, there are ways for charging for the electricity. Most states have said for electric vehicles, there's an exception. Normally you can't resell electricity, but for electric vehicles, it's a different story. A building can make up its own rules of what it's going to charge its occupants for charging their cars. So anyway, This might apply to restaurants, this first one, for example, because chances are if the car is plugged in for an hour and a half, people are going to leave. So then somebody else can use it. So if you can have multiple users of a single charger, then you don't need as many chargers. Pretty straightforward, but you got to do some interesting observations here and maybe some field studies to figure out what's going to work best. All right. Um, Certainly, unless you had a parking attendant in a multifamily residential unit, nobody's going to be out there at night saying, okay, 105, your car is charged, next 106, next 107, 201, 202, whatever. Um, nah, nobody's going to do that. So better let that be done electronically. Anyway, for restaurants, that's another story. And lodging occupancy. If you have a parking attendant and a monitoring system that tells when the charge level's up there, these are situations where cars are going to be parked probably a whole lot more than 1 or 2 hours, but maybe in 5 or 6 hours the car gets filled. So if there's one attendant and 12 parking spaces or something like that, it shouldn't be too hard for that attendant to move around some cars. On the other hand, you have to decide, do we want to do that, or do we simply want to have more charging stations that talk to each other with the same number of circuits and the same amount of power available, but simply an equitable distribution of charge amongst these vehicles? And so, given that the owner might want 200 miles of charging, that's 7 hours at level two. So that's why the parking attendant thing could work, and you just give the guy a tip for moving. Well, they'd get some pay, but then you'd pay for thank you for moving my car, so I didn't have to get up and do it myself, or something like that. So it takes a little thinking and so forth. Level threes, great on long trips, and we had talked a bit about that. Uh, nice for rest stops. And there are even higher power units available. 434 amp circuit. If you're, then basically, this is, there's no 450 amp circuit breaker. You're going to have 500 amp circuit breaker here. That's a 500 amp circuit. If you're going to go at 125 kW at 208 volts. So, that's big time stuff and big time transformers. And so you don't just put these anywhere. You got to work with utility on these things. Um, if you have a 600 volt delta connection, then the current drops to 120 amps. And that means you can have a 150 amp circuit at 105%, and that's a little more practical than a 120 208. The other thing you need to look at is what's the DC output voltage and current going to be on the 125 kW charger. For 1,000 volts, that means charging current is going to be 125 amps if it's 125 kW, because that's 125 times 1,000 is 125,000. So that's going to be your charging current at 1,000 volts DC. That's heavy duty charging, pretty big cord, big plus, big minus, and that's why people love to go steal them, apparently. I've heard about that. Lots of copper, whatever, even if it's aluminum, it's almost worth salvaging as long as you don't get a big shock. So you have positive, negative, and equipment grounding conductor in that cable. So in any case, AC and DC, level 3, going to have pretty high charging voltage. And level 3 charging is done at DC, but the AC has to be converted to DC. So generally, you're going to have fairly high voltage coming in as well before it gets rectified. So what else do we want to think about? What if the service is inadequate size? Well, make it bigger if you can, or maybe install a new one. Might even need a new transformer up on the pole. Who knows? It's something you might need to talk to the utility about, or maybe a new pad mount somewhere. Uh, might be some delays due to demand for new services. And what about systems interacting? How about the deal? What might be some of the questions here? Well, it's certainly possible. We know that the protocols are already established. And what if photovoltaics with energy storage is involved? Well, uh, Tesla and Enphase certainly have got some good solutions for this, and I'm sure that some of the other manufacturers do as well. Simply that uh, if you got battery storage, you can let your battery in your car be part of that ESS, or your your system can be programmed so that if it's not supposed to be exporting to the utility, then any extra photovoltaic power at midday when it's peaking out would get dumped into the batteries of either the car or elsewhere. So those kind of programs can be uh, implemented on the equipment. So it's a matter of, once again, what's your jurisdiction, what's your utilities, what are their rules, what are they willing to deal, how are they willing to cooperate? It turns out uh, utility can benefit as much from the EV owner as the EV owner can benefit from the utility. So about time we start talking to each other and coming up with some good agreements. Um, Charger and the battery system and the solar are likely to have communication links. And we know that pretty much all of them do, or at least they're available. Read the installation manual, really important. Read the equipment specs. Know what you got available. And also keep in mind that if when you're charging at home, if somebody is going to maybe they drive 20,000 miles a year, but 10,000 miles of those get charged out of the away from the home because they're far away and there's no way they can come back home to charge at night. That needs to be taken into consideration as well. So it's not just a matter of how far you drive, but how many times you go away from home and charge elsewhere. So questions to ask, even simple level one chargers have cell phone communication. So you can get charging data on your phone. And these things are rapidly evolving. Um, Power management, billing, and consumption data, extremely useful properties. And especially useful for condominiums if they want to charge the owners. It's out there. This can be done. Just have to, somebody says, hey, we want to do that. Power management can be helpful for chargers connected to services, but particularly to multi-unit meter centers to prevent overload of the main meter center feeders or for demand control. Bi-direction, it's gone away. Give it 1 or 2 more years. Lots of ways to pay. Some is free. A friend of mine just bought a new electric vehicle and he's got 2 years of free electricity with it. He has to go elsewhere to charge it, but he's perfectly happy to do that. And he doesn't charge every night. He just fills it up a couple times a week, like a regular gasoline car. But he has to drive away from home to do that. But again, you do that with the gasoline vehicle as well. So, a lot of different ways to pay. And a lot of different incentives of restaurants either giving free electricity or whatever. So a lot evolving there. Uh, Two of the load control methods is the uniform distribution method, which simply says if we got 8 cars, we're going to give each of them 1/8 of the available power. And we simply maintain the total of all charger outputs at less than the preset maximum. And this works nicely with fleet charging. The other algorithm is first in, first serve, which says the first guy in gets charged as fast as they can until somebody else comes in. And then it slows down a little bit and lets the other person start charging. Um, or it can actually charge up the first one completely before the second one's connected in. Again, you decide, you do the program. Depends on the location, the application, and so forth. Pull up a vehicle, next one gets power, whatever. And all this stuff, as we've mentioned numerous times already, that's especially useful for overnight charging. Because it's really nice if you don't have to move the vehicle. So therefore, let's put a little bit of intelligence in the system itself so it's smart enough to charge everybody. And if it has some idea when people arrive and leave, and if there's any regularity to that, or if people can simply inform the system ahead of time what their plans are for the next day, it helps the system. And all that is possible to do. If ChatGPT is possible, then this kind of stuff is a whole lot simpler. So, Blink is one company, and I don't work for Blink. I don't have any, but just happen to look up Blink if you want to get some details on a data sheet. Um, this is what Blink offers. All right, and but Blink, they're not the only guys in town. Uh, but this kind of stuff you can get. So what's happening with the EV chargers? Well, they're going from this to this, and pretty straightforward. We've hinted that all through. But either one, with proper demand management, can be useful to the utility. Even on a one-way charger, if it's set up so that when the utility has excess renewable energy that it would like not to curtail, if it can dump it into somebody's battery pack, it would be a whole lot happier to sell it to somebody rather than just curtail it and not be able to sell it at all. So, um, that's a no-brainer. And again, I say it's the beginning of the story because there's a whole lot more going on. Who knows what's going to happen? Ford's quitting their production maybe. Over in Norway, though, they're, as of 2025, supposedly the only vehicles they're selling are electric vehicles. So we're in a very interesting time right now in this country. Um, the Chinese, on the other hand, building electric cars, using them themselves. Other people are buying them, but we aren't. Going to be an interesting world for the next 4 or 5 years, 10 years, 20 years, however long you plan to hang around. So don't tune out. Be sure to pay attention because it's certainly going to be interesting. And I just say the beginning of the story, end of webinar. If anybody, we've got 5 minutes. If anyone wants to discuss anything, let's open it up for discussion. Anybody have any comments, any questions, personal experiences? Love to hear from you. I'm going to open my Q&A and see. Okay, right now I see no open questions. If you want to use chat, that's okay. If you want Q&A, I've got my Q&A open, so I'm watching for that. But I see something in chat, which may be from the host. Yeah, that's from the host. So let's just give another minute and see if there's anything popping up in Q&A. I don't see anything. Hisham, everybody must have fallen asleep, man. I'm sorry. Or else they understood everything perfectly. Well, anyway, keep in mind that after this last slide, there are a few appendix slides that go in a little more detail on how the three-phase currents add up, if that's of any interest to you. Otherwise, let me just say thanks for joining us this afternoon. Hope you have a great holiday season, and uh, in shorter term, I hope you have a nice dinner tonight. All right, I'm going to stop sharing my screen, but I'm going to hang on. I'm not going to sign out, and I'm going to watch my. All right, here's chat. Yeah, California power is really expensive. You bet, close to 30 cents a kilowatt hour. Uh, all right, and the hub is saying this is it. So once again, uh, don't forget to do the quiz. We appreciate any feedback in terms of the material itself. Encourage you to fill out the evaluation. Feedback is what leads to better product. I've relied on that for the 35 years I spent as an engineering professor, and I still rely on it. I like to get stuff right and get it in a form that people can make some sense out of it. All right, thank you very much. Time to sign out.